So I'd like to thank the organizers for inviting me to speak at this nice conference in the city of Montreal, which I also find very nice and friendly. Good to find Paris away from Paris in North America. But actually, before I start, I'd also like to thank the people of Canada for their support of Ukraine in this horrible ongoing war with Russia. I was born in Russia and grew up there. As Alexander Solzhenitsyn, famous Russian writer and Nobel Prize laureate, said, governments need victories and people sometimes need defeats. So I think Russia could use right now a defeat to come back to its senses. Well, as for physics, I will talk today about thermodynamic phase transition in random field Ising model and related models in d dimensions in presence of field disorder. So I guess this subject is not probably very familiar to many people in the audience. So just to get a show of hands, how many people heard about Parisi-Sourlas Supersymmetry? Quite a few people. So, but still, it's not really the focus topic of this conference. So I'll try to be pedagogical. So mostly I'm interested in field disorder, but I'll, at least at the beginning, it's good to consider, to contrast two models, two different types of disorder. So I will contrast, to begin with, the bond disorder, where you take the Hamiltonian, it's a classical Ising model for magnetic. So you take a sum J plus delta J xy as x as y over, say, nearest neighbor. And in the bond disorder, you have this random perturbation of the coupling, which has mean 0. While in the field disorder, you take and you add the Ising Hamiltonian, you add a random magnetic field, again having average value 0, and some non-zero h squared average. So we have these two models, and they have rather different behavior. So the bond model is much simpler to treat. So first of all, I'd like to remind you why this is the case. And it's easy to understand using the language of field theory, which I will use most of the talk. So let's just go to the field theory description appropriate near the phase transition. So I'm going to write the effective Lagrangian, and it's going to be, for the Ising model, it's d phi squared plus v of phi, where this is some quartic potential, square phi squared plus g phi to the fourth. And now, if I want to consider disordered theory, I add to this some disordered coupling J times O, where J is the source, so it has some average value 0 and some non-zero two-point function. J of x prime average is h delta of x minus x prime, where h is the parameter which is the disorder strength. And the operator O, it depends whether you are considering field or bond disorder. So O equals phi squared would correspond to bond disorder, and O equals phi is field. Then, as a next step, we are going to the replica description. So we take the action and go to S1 plus Sn, where these are where they just take sum of d phi I squared plus v of phi I plus the same source times O1 plus On. So I'm supposed to take n going to 0 limit. And then when I take the path integral, over the source, let's suppose it's Gaussian simplicity. So I integrate over J.
Bar phi and I are the same, right? Because in the quadratic term, you have a bar phi.
Bar phi.
Yes. And in the
okay. You mean this is the curly and this is the straight?
Yes.
No, it's the same for the moment. Yeah. Sorry. Just sometimes it's the hand draws like this. sometimes.
Also about, you wrote as well in the previous whiteboard.
That's why.
Yeah, for some reason here I always write a curly one. Maybe it's because this curly and then you like kind of
Never mind.
inconsistent.
Never mind.
So here, so you integrate over J and you get this term minus H or 1 plus ON squared when you integrate over J. And so now we have to understand if this perturbation is relevant or irrelevant. And if we are considering bond disorder, so O equals phi squared, then what do we have? Suppose that we are in 4 minus epsilon dimensions. Then suppose that you just treat this perturbation around the critical point of the Ising model. Then at the critical point, the dimension of phi squared is equal to twice 1 minus epsilon over 2 plus the anomalous dimension epsilon over 3. So it's 2 minus 2 epsilon over 3, which is smaller than d over 2. So I'm actually in this term, I can focus on the cross terms or I or J, with I not equal to J. And so I have to consider if these cross terms are relevant or irrelevant. So that's why the criterion is that the dimension of phi squared has to be smaller than d over 2. This is the Harris criterion. And so in 4 minus epsilon dimensions, this Harris criterion is satisfied for the bond disorder. So this means that adding this perturbation, we are going to flow to a different universality class.
If O is phi squared, then the theory is quadratic.
Well, here it is quadratic, but it's coupled to the random source. So before you eliminate the random source, you cannot just take advantage of the quadratic nature of the theory. But once you eliminate the random source, it's no longer quadratic, it's quartic. Because you have O1 plus ON squared. So what was phi squared became phi to the 4th. What right now I'm just trying to understand, okay, what is the nature of this coupling? Is it relevant or irrelevant? So I just showed to you that in 4 minus epsilon dimensions, it's already relevant. As you go to 3 dimensions, then we know that the dimension of phi squared is approximately 1.41. And so again, it's smaller than 1.5. So again, this perturbation is relevant. So what this means is that, okay, first of all, it means that we changed the universality class. But on the other hand, this change is not dramatic because this perturbation, even though it's relevant, it is weakly relevant. And so, for example, if you are in 4 minus epsilon dimensions, well, you just have an extra quartic coupling to consider, and you have to look for a new fixed point where this extra coupling is turned on. You can also do conformal perturbation theory in 3 dimensions. Again, it's a weakly relevant perturbation. And so what it means is that in this case, you actually have, so one interesting property is that in this case, you have a family of CFTs which depend on n. So for every n, you have a CFT. So you can compute critical exponents if you would like to compute critical exponents. You compute them as a function of n, and then you go to n going to 0 limit. That's for the bond disorder, that's a totally legit operation.
So you're flowing from the Wilson-Fisher point to this new point.
You can flow from Wilson-Fisher point to this new point from disorder, or you can flow from the Gaussian theory to the new point from disorder. But so that's a simple case. Now I would like to contrast it with the field case. So in the field case, you follow through the same procedure. So you get the perturbation minus h phi 1 plus phi n squared. So this perturbation is strongly relevant. So it is relevant. So we do change the universality class, but it is strongly relevant. So you cannot simply use perturbation theory in the same way as we can use it here. So that's going to be my main case of interest. And in this case, you have two dramatic consequences, as I will explain. So the first thing is that you actually do not have, so you do not have t for every n. Rather, what you have is that if you take n, which is small and close to 0, you have a theory which has a mass gap. So for n small non-zero, you have a mass gap, but then this mass gap goes to 0 as n becomes smaller and smaller. And so in the limit when n goes to 0, you recover the scale invariant theory. And so you can compute the critical exponents. So this complicates. And another thing which is different from this Bond-Desargues case is that we see that in this Bond-Desargues case, the critical dimension is 4, the upper critical dimension, just like for the Ising model. While in this case, the upper critical dimension is going to be equal to 6, as I will explain. And so, okay, how do you see these two things? Well, the first thing that n small causes a mass gap, you can understand as follows. So let us look at the action of the theory. So we have the kinetic term, sum of d phi I squared. And now, okay, we have some mass term here inside the potential, and we have this new term, which is also quadratic. So when you compute the propagator, like, okay, the natural thing to do is to compute the propagator, taking into account also this new quadratic term. So that's, of course, very standard. So, and when you compute this propagator, phi I, phi j, then in momentum space, you find two terms. The first is just the usual propagator, j over p squared plus m squared. And then the second term that you find, it's proportional to h. And in the denominator, you have p squared plus m squared, p squared plus m squared minus n times h. And so you see that, okay, to make the theory critical, we tune the mass to 0. But here in the second term, we see that we have two poles, and we cannot set both of them to 0 unless n is equal to 0. So that's one way to see that there's not going to be really, you cannot really compute critical exponents by analytic continuation n. You really have to go to n equals 0.
So there are no index in the second term?
Well, there's some matrix here, Mij, which has all matrix elements equal to 1. So Mij is equal to 1 for any ij. Okay, that explains the first thing. And now, what about the second thing? So there are some textbooks explanations of this second fact that the upper critical dimension is equal to 6. And you can find them, for example, in Cardy's book. And they go as follows. So you say that in this theory, you actually have two couplings. There is a quartic coupling here, which sits inside the quartic potential, and the dimension of the quartic coupling is equal to 4 minus d. And then there is this coupling H, which has dimension 2. And then there is this claim that the effective coupling that you have in this theory, G effective, is actually the product of the two, G times H. And so it has dimension 6 minus d, and it becomes marginal precisely in d equal to 6. And so that's the textbook explanation of the upper critical dimension of this model. And the reason, the way you convince yourself that G effective is the true coupling is that you compute some Feynman diagrams, corrections, and somehow whatever you do, it's always this product G times H which comes up. So you check a few Feynman diagrams, you say, well, it looks like that's the right coupling. So, when I first encountered this problem of the random field Ising model 2 or 3 years ago, I was not particularly happy with this explanation because, when I look at the theory near the upper critical dimension, I would like to see one coupling which is getting marginal. I don't want to see like two couplings, one of which is irrelevant, another is relevant, and somehow their product is a marginal coupling. So I really would like to be ideally see one coupling which is getting marginal, and in this picture somehow this is not available. And so in our work with Août-September and Emilio, Août-September is now a postdoc in Desi and Emilio is a postdoc Paris, we found such a picture. So we developed such a picture, and as I will explain, this picture is very useful to explain some puzzles related to this random field Ising model, namely related to this Parisi-Sourlas Supersymmetry. So
can I ask a question? So,
sure.
is there any simplification considering D equal 4 or higher, I would say 5? I mean,
No, there's no simplification. Okay, so what is kind of behind this difficulty, this puzzle of different scaling dimensions? So if you take this propagator that I already wrote here, and if we go to if you take m squared equal to 0, and if you take n equal to 0, then this propagator becomes delta ij over p squared plus h over p to the fourth. You see, it's a propagator which is not a pure power law. So this means that this multiplet of the fields phi I, it's actually a mixture. This field phi I doesn't have a well-defined scaling dimensions, but rather it is a mixture. It is a sign that phi I is a mixture of fields having different scaling dimensions. And so this fact, as well as some intricacies of n going to 0 limit, they actually change the dimension of the quantic coupling. So that's the claim. And so the first computation that I would like to show you, to convince you that that's what's going on, let's just take the quantic coupling, sum of phi I to the fourth. Let us just try to make an honest calculation of the dimension of this operator. So how do you compute the dimension of an operator in quantum field theory?
So this is phi I to the fourth, not phi I square.
Not phi I square, because I'm now studying for the rest of this talk, I'm only going to be looking at the field disorder.
Yeah.
So my Lagrangian is maybe
Sorry.
maybe I should write down my Lagrangian. So it's d phi I to the fourth, the squared, sorry, plus, well, their mass term, but let me not write it down, g phi I to the fourth. So this is summed from 1 to n, and then minus h phi 1 plus phi n squared. So let me take this operator and let me ask, what is the scaling dimension of this operator? So how do you find the scaling dimension of an operator in quantum field theory? Well, one way to do it is to compute a two-point function of this operator, say in position space or 0 of x. And then this two-point function, is going to go as a constant over x to the 2 delta, where the dimension delta is the dimension of the operator. So unfortunately, in our case, this method is not going to work, because since O is a sum of n fields and n is going to 0, if you compute the two-point function and if you take this n going to 0 limit, you will find exactly 0. So any singlet operator in the n going to 0 limit is going to have a 0 two-point function. So this method doesn't give you the scaling dimension. But there are other ways to find the scaling dimension. For example, you can consider the OPE of operator OX with itself, and you can ask for the coefficient with which the operator O appears in its own OPE. And so that coefficient is also sensitive to the dimension of the operator O. So it's a constant over x to the delta. And for this coefficient, the fact that n is going to 0 doesn't say that this coefficient has to vanish. So you can really compute this coefficient. And so what? So how do you compute this? How do you compute this prefactor? Well, yeah.
Why you expect now this operator to have a defined scaling dimension if phi is not?
In fact, it's not going to have a well-defined scaling dimension, as we will see in a second. But at least you can ask yourself, okay, that this operator is not an operator of well-defined scaling dimension, but what is the least dimension component inside this operator? And that thing should be relevant.
And is there a particular reason why we're considering this operator?
Well, because this operator is our interaction operator in the Lagrangian. So that if this operator, this is the interaction, if it is relevant, then we are going to have a non-trivial fixed point. So this is now, this becomes a rather trivial calculation. I just have to take an OPE of roughly phi I to the fourth and phi j to the fourth, because I'm summing, okay, once over I and once over j. And I have to look here in the right-hand side for something which is quartic. So that's the standard, no, I just have to do twice the V contraction. So I have to do phi I, phi j squared, and then there's going to be phi I squared, phi j squared. You know, if you've done these calculations, you know how this goes. And so now, so we have the propagator in momentum space. You can transform it to the position space. And now what you see is that the important term is going to be the cross term when delta ij times h. So if you just pick a term which is proportional to h, then you don't get anything interesting, because that's going to be, so in position space, this becomes delta ij over x to the power d minus 2 plus h over x to the d minus 4. And so the important term is going to be delta ij times h divided by x to the 2d minus 6. And so this, because then when you contract this delta ij with phi I, phi j, you get precisely what you need, phi, you get phi to the fourth. And so you see that there is this 2 delta minus 6. It is the dimension of, well, let me call it, yeah, it is the dimension of the operator that we are looking for. But now coming back to your question, Paula, this is not the only term that you will find. There's also going to be a term delta ij divided by 2d minus 4, because from the square of this term. That's also going to be there. And since the term is present, it means that this 2d minus 6 is just the lowest dimension part of the operator. You see, we recovered the upper critical dimension again, because 2d minus 6 becomes marginal for d equals 6. This computation is still rather awkward, as you should agree, because because I'm dealing with operators which do not have a well-defined scaling dimension. So I still have not resolved this this issue. And so to make progress, we have to solve this once and for all. And so let me show you how this is done.
You could write that the P4 like a difference of P square. No, it's a P4 is a non-unitary.
Everything is non-unitary.
Okay.
Yeah, because we are in a disordered system, so the model is non-unitary.
So, two questions. In this application, why isn't there an h over 2d minus h squared over 2d minus whatever they say?
Because that gives a different operator. That gives an operator. So that instead of producing O in the right-hand side, it produces me sum of phi I squared. Yeah, you need the product of delta. And so what we really need to do before to simplify our life is to find a linear transformation from the fields phi I, which do not have a well-defined scaling dimension, to some basis of fields which do have a well-defined scaling dimension.
Yeah, that's what I was saying.
That's what you were saying?
Yeah.
Good, good. So you were saying the right thing. Bravo. And this transformation takes the following form. Actually, several one, but this is the simplest one. So now finally I have to keep the difference between curly phi and straight phi. So So it's a bit fishy, this transformation, but let me just write it. So phi 1 is equal to curly phi plus omega over 2, and the other phi i's are curly phi minus omega over 2 plus chi I. So this is for I from 2 to n. And so I'm transforming from phi i's to three fields, phi, omega, and chi I. And to conserve the number of fields, I'm also imposing the constraint that sum of chi i's is equal to 0. So this funny transformation, it was first considered in a little known paper by John Cardy in '85. And it does exactly what we need. So if you take this transformation and if you plug it into the Lagrangian with which we are dealing, this one, then you will find that the quadratic term in the Lagrangian gets transformed into the following thing: d phi d omega minus h omega squared h over 2 plus 1/2 d chi I squared plus something which goes as terms of order n. Okay, let me just show you one thing. So I don't want you to give you the full transformation, but let us just do this transformation for the sum of phi i's. So if you take the sum of phi i's and we do the transformation, so phi 1 gets phi plus omega over 2, and you get all the other i's, of which there are n minus 1, which get multiplied by curly phi minus omega over 2 plus chi I, but chi I sum to 0, so we can drop them. So that's what you get. So now let's see, we get, this is n times curly phi plus 1 minus n over 2 omega. So this goes to omega. So this is omega plus order n. And so this reproduces us this term. And all the other terms are, you land on this beautiful Lagrangian. And in this Lagrangian, all fields, so you have three fields, phi, omega, and chi I, and they all have well-defined scaling dimension. In fact, they all have well-defined scaling dimension, and they are not equal to each other's scaling dimension. So you get that the dimension of omega is equal to d over 2. The dimension of chi is equal to d over 2 minus 1. And the dimension of phi is equal to d over 2 minus 2. And also you can write down propagators, so phi omega, phi, things like that. This is the quadratic action. We have quadratic action where all fields have good scaling dimension. So now, good, we have the good basis of fields. We now transform all the other interactions to this basis. Particularly the phi to the fourth. So that's the one that we started with. So you take some phi to the fourth, you transform it to this, you do this transformation, and so what do you find? You find 4 omega phi cube plus 6 omega squared, no, plus 6 phi squared chi I squared plus higher dimension terms. And so we see that we just beautifully recover our conclusions there, because if you look at this omega phi cube plus 6 phi chi squared, both of these terms, they have the dimension 2d minus 6, as we predicted. And then we also discovered that there are some terms of higher dimensions that they also exist. So just like from that argument, but it's a much simpler way to recover this fact. And so that's it. So after Cardy transform, the random field Ising model Lagrangian, it becomes a sum of the quadratic term, which is written there. I'm not going to rewrite it. And okay, there's going to be a mass term and the quartic interaction, which is this one. And we drop the higher dimension term because they're irrelevant near the upper critical dimension.
Is there a problem that potential is not bounded from below?
Well, there's no problem. So if you want to do things like very cleanly, rigorously, you have to integrate out this omega. And then once you integrate it out, you get something which has a good potential. Everything is very bounded. There's no problem. I mean, bounded. It's going to be bounded once I do this next step in the argument, because right now we are still dealing with the theory which has -2 fields chi I. But now we come to the next step in the story. So I can now introduce this beautiful Parisi-Sourlas Supersymmetry. Originally was introduced in a completely different way by Parisi-Sourlas, but this is the cleanest way to arrive to it, and it's also the cleanest way to understand what may go wrong with this argument. So I have this Lagrangian which has the field chi I, and the field chi I, there are n minus fields satisfying one constraint, so there are effectively n minus 2 fields. So in the limit n going to 0, I have -2 fields chi I, which are scalars. And you see that these fields, they enter quadratically in the Lagrangian, both in the kinetic term and also in the interaction. And so what I can do now is I can say that having -2 scalars is exactly the same thing as to have two anti-commuting scalar fields psi and psi bar. So these are anti-commuting scalars, Grassmann fields. And so once I do this, I get a Lagrangian which has the following form. So d phi d omega minus h over 2 plus d psi bar, quadratic term. And also here I get plus 4 omega phi cube plus 3 omega squared psi bar. Now, once you have this Lagrangian, you notice that this Lagrangian can be written in a manifestly supersymmetric form using a superfield. So you introduce this superfield big phi, which is a linear combination of phi of x. So it depends, the superfield depends on x and on two Grassmann variables, theta and theta bar. So it's phi of x plus theta psi bar plus theta bar psi plus theta bar omega. And in terms of this superfield, you write down a manifestly supersymmetric Lagrangian or action, which is integral over d dx d theta bar minus 1/2 big phi, some Laplacian operator in superspace phi plus v of phi. So if you use the superspace rules, and if you integrate out theta and theta bar from the superspace Lagrangian, you land exactly on this Lagrangian written here in the components. So this way tells you that your theory has a supersymmetry. And once you have the supersymmetry, the next observation that you can make is that the theory is supposed to have this property called dimensional reduction. So dimensional reduction is a consequence of supersymmetry. It can be understood in different ways. It can be understood as some sort of supersymmetric localization.
Actually, the supersymmetry from the correlation function just computed, and then it goes to zero limit. Like if I don't do this transformation.
Yeah, you can see. So if you are supersymmetry, interesting thing about supersymmetry is it's valid also for the interactive theory. But if you just want to like let me set here is the coupling constant, which I forgot. If you set the coupling constant to 0, you just have a free theory. The free theory also has, of course, supersymmetry. So you have to work out the supersymmetry transformations, which are just super translations, super rotations.
I don't do the supersymmetry transformation. If I don't write down the theory in terms of phi, then I still so I start with the Rychkov like I have like phi from 1 to n, right? And then I can use that Rychkov theory to compute some population functions. So from those results, can I see there is a supersymmetry in it?
Well, you see, to talk about supersymmetry is a symmetry which relates bosons to fermions. So you have to go to formulation of the theory where there are fermions, there are Grassmann fields, and then you can define what you mean by supersymmetry. You can check whether it's there or not. If you don't go to this formulation with psi's and psi bars, if you just stay with the formulation in terms of chi's,
Right.
there you don't see the supersymmetry.
But is there any indicator for supersymmetry?
Yeah, you will see some, of course. You can derive some, for example, relation between the correlation functions of phi and phi omega. And those are two correlation functions involving bosonic fields. They will totally be consistent with supersymmetry, but you won't be able to derive them using supersymmetry, because in order to derive them, you have to pass through psi. And psi is not a part of that of your theory, so you kind of use the link.
It's like the supersymmetry is a property. It's because we write the theory in a certain way.
Yeah, it's not manifest. You see, it's a symmetry which sometimes in that description is not manifest, and you make it manifest by going to this description. Yeah.
But the dimension reduction is more intrinsic than the supersymmetry.
Well, dimension reduction is you won't be able to understand dimension reduction unless you go to the SUSY formulation. So it would be completely mysterious.
But why do you say that minus the scalar field is equal to plus a fermion?
Because since the fields enter completely quadratically, right? You can integrate them out. You get a determinant to the power, which is the number of fields. Since you have minus 2 fields, it's a fermionic determinant.
Okay.
So
Another question about the supersymmetry. Is this a space-time supersymmetry or is it just a fermionic?
it's a space-time supersymmetry. It's not in that sense. So it's when I meant that it's space-time, meaning that it's not like a global supergroup symmetry. So it's definitely a supersymmetry transformations. They involve derivatives of the fields. So it means that they shift points around. So the rotation, the algebra in this OSP d/2 space in which we are, which involves the rotations and super rotations. So there is some spatial part involved. But there is no relation like supercharge squared equals P, which is familiar from supersymmetry with fermionic generators. There are other relations, but they're not that one.
Not super factorial.
It's a different superalgebra. Yeah, it's a much simpler superalgebra, in fact.
What is it?
It's OSP d/2 times the Poincare times the translations. So, but in fact, I didn't want to talk much about the supersymmetry and its consequences. I just wanted to mention that the dimensional reduction says that if you take this theory, the Parisi-Sourlas supersymmetric theory, and you set everything to a d-2 dimensional subspace, then the theory becomes equivalent to a d-2 dimensional theory with the same Lagrangian, -1/2 phi box phi plus v of phi. In particular, if this theory flows to a fixed point, then this theory also going to flow to a fixed point, and this fixed point, or vice versa. And since this fixed point is going to be the Ising fixed point, this implies that the critical exponents of the random field Ising model in d dimensions, they have to be exactly the same as the critical exponents of the normal Ising in d-2 dimensions. And as I said, this could be understood as some sort of supersymmetric localization when you rotate around this RD-2 plane, or in our work, we gave a different understanding of this in terms of some sort of cohomological OPE reduction. For experts, this is a bit similar to n=2 chiral algebra story that was developed by Leonardo Rastelli et al. So there are some interesting ways to understand this, and we think that this part of the story is on solid grounds. Really, if the theory is Parisi-Sourlas supersymmetric, then the dimensional reduction follows. However, as you know, many of you I'm sure know, something is not quite right, because numerical simulations, and over the years there have been increasingly precise numerical simulations. And so right now, I think the best simulations are by Fitas and many other people, which also involve, I think, Martin Meyer. Let me write everyone: Martin Meyer, Sourlas, Pico, and Giorgio Parisi himself also participated in this work. So these numerical simulations, they show that the dimensional reduction doesn't work for d equal 3 and 4. There is no dimensional reduction. While for d equal 5, this is a more recent finding, they actually see dimensional reduction, and they also see evidence for SUSY. And so how can we come to terms with all this information? The most natural conjecture that any reasonable RG person would make, given this data, is that something like the following should be going on. So if we consider, as a function of d, the theory, let's say, 3, 4, 5, 6. So what is the picture in the theory space? So which fixed points do we have in the theory space? For any d, we have a Gaussian theory, which is the Parisi-Sourlas free theory. It exists for any d. Then, as we discussed, for d less than 6, the supersymmetric interaction becomes relevant, and so you have a line of new fixed points which splits off. So here we have a line of new fixed points. So these are interacting Parisi-Sourlas fixed points, and these Parisi-Sourlas fixed points, they should exist for any d up to d equal 3. So in d equal 3, really Parisi-Sourlas supersymmetric fixed point doesn't exist, because for d equal 3, that fixed point would be equivalent to a d equal 1 fixed point for the pi to the 4th Lagrangian, which we know doesn't exist. So this line here, this line terminates just before d equal 3. But then how can you reconcile this picture with this numerical information? Well, what should be going on?
Why not d equal to 4?
For d equal to 4, the Parisi-Sourlas supersymmetric fixed point definitely exists, and it has the same critical exponents as the two-dimensional Ising model. For 3, for 3, okay. So what we should imagine, what we should conjecture is going on is that there should exist some instability. So there should exist some critical dimension, let me call it DC, which below which this line of supersymmetric fixed points becomes unstable, so that for d equal 4 and d equal 3, sorry, this plot is not very good. So for d equal 4 and d equal 3, the random field Ising model is described by some other fixed. So now the goal of the theory should become to understand this instability. What is this instability? But as you could now imagine, with this beautiful Cardi transform that I explained, this problem is totally accessible to standard quantum field theorists. So this problem can be addressed, and that's what we did in our work. Actually, how much time does it have?
10 minutes.
Okay, good. So what do you need to do? Which effects may destabilize the fixed point? Which SUSY breaking deformations can you consider? So the thing is that when we went from from the Cardi transformed Lagrangian to the Parisi-Sourlas supersymmetric Lagrangian, we did two things. First of all, we did the Cardi transform, and we dropped various pieces of the Lagrangian because we thought they were relevant. Then once we dropped them, we did this transformation going to psi and psi bar. But this dropping terms, of course, is good only if the terms which we thought were irrelevant are really irrelevant. And those terms were definitely irrelevant close to d equals 6, but who knows what happens to them as we start lowering dimension. This needs to be computed. But you have to be a bit systematic because you don't really know which, you don't really know a priori which interaction is going to be the problematic one. And so what you should really do is that you have to go to the symmetry of your theory. The theory before we did the Cardi transform, the symmetry of the theory was Z2 times Sn. So what we should really do, we should consider like all possible interactions which are consistent with the Z2 plus Sn symmetry. Let me call them singlets. We take these interactions and we, like each of them, we transform to the Cardi basis. So once you do this, when you transform any interaction, any single interaction to the Cardi basis, you will get several terms. The first of these terms, the terms with the smallest scaling dimension, we call a leader. There's going to be a leader term, and then there are going to be some further terms that we call followers. But those follower terms, they have scaling dimension equal to the dimension of the leader plus 1, plus 2, and so on. So what you can convince yourself is that in order to study the scaling dimension of the interaction, you can just compute the scaling dimension of the leader interaction, because all the other ones, they go for the right. And so that's what you need to do. It's a well-defined quantum field theory problem. You classify the leaders, compute anomalous dimensions for the leaders. Does any leader become irrelevant? Sorry. So, well, you have to, of course, there are many operators and they mix. So this is a complicated problem. You have to classify things a little bit. So there's a classification of leaders that we developed. We classified them into 3 types. So there are SUSY writable leaders. SUSY writable leaders are the ones that involve chi's only in the square, only bilinear. So they involve only things like chi squared, and so you can transform them into the supersymmetric notation by replacing chi's by psi's. So this is like this vortic interaction, for example. It had a SUSY writable leader. So these are the simple guys, the SUSY writable leaders, because you can use supersymmetry in order to relate their scaling dimension to the dimension of operators in the Ising, in the 5 to the 4th theory. And of course, a lot is known about operators in the 5 to the 4th theory, so you don't have to compute anything. You can recycle the existing results. But now there are these other 2 classes of leaders, one which we call SUSY null. So SUSY null leaders.
Formation created by SUSY variable operator, do they still preserve the supersymmetry?
No, because these are not, these are some components. So these leaders, they are some components of a superfield. So if to preserve supersymmetry, you have to add a particular component. If you add another component, which of course has a dimension related to the other one, it may not necessarily preserve supersymmetry. But still, your scaling dimension you can still control. Yeah. So the SUSY null leaders, they are funny ones. So these are things like chi I to the 4th. So this, once you go to the SUSY formulation, it becomes psi bar squared, which is 0, of course. So these operators, which you can transform into the SUSY basis, but they vanish there. Since they vanish, you cannot use SUSY to compute their anomalous dimension. So you have to compute them from scratch. And then finally, there are some things which are called non-SUSY writable. These are things like chi cube, sum of chi cube. For example, there's an operator sum of chi cube squared minus 3/2 sum of chi squared chi to the fourth. So this guy, you cannot even transform it to the SUSY. You just cannot transform chi cube to the SUSY field. Impossible. So again, this sort of operators you have to treat from scratch. And the interesting thing is that these two leaders, the SUSY null leader and the SUSY non-SUSY writable leader that I wrote here, these are precisely the first two fields which are families of some operators that were considered by Feldman in 2000. Feldman, he a little bit took this operator out of the hat, but he was right that these operators are important. So we did not follow Feldman's logic. We just considered symmetry considerations, and we considered as many operators as we could. We classified all leaders up to some very high scaling dimension, like hundreds of operators. But eventually, we found by the systematic search that these F4 and F6 indeed are the important operators of this theory. And what we did is that we computed anomalous dimensions of these operators, and we found that it is that these operators F4 and F6, their leaders get negative anomalous dimension at two loops. So they have a pretty high classical scaling dimension, but they also have a rather large two-loop correction. And so if you take the scaling dimension and if you plot, so this is the money plot as a function of D 654, then you find that these two operators, they cross marginality around D equal 4.5. And so we think it's a satisfactory result because we really find two operators which can possibly become which can perhaps become relevant around this dimension. So this matches very nicely with the numerical. And our scenario has a smoking gun because what we predict, this is different from some other people who thought about this problem before us, is that in D equal 4, so our prediction is that below D equal 4.5, this fixed point, the SUSY fixed point, becomes unstable. But it still exists. The Parisi-Sourlas interacting fixed point still exists in 4 dimensions. It's just unstable. So if this is the case, then it should be possible to find this fixed point in a numerical simulation by performing an additional tuning. And so what kind of tuning can you perform when you simulate the random field Ising model? Well, whenever you simulate this disordered models, you have to pick the disorder distribution, the shape of the disorder distribution, which can be, for example, Gaussian. Okay, most people pick Gaussian, but that's not the only distribution you can pick. For example, you can pick like a two hump distribution or something like that, or you can interpolate between one and the other. So this gives you some tuning power. And so the smoking gun prediction that we are making is that by doing this sort of tunings, you should be able to find this Parisi-Sourlas supersymmetric fixed point in a numerical simulation. And actually, when we wrote our papers, we put there this section about the smoking gun because it's important to have smoking guns. But frankly, I did not have much hope that the numerical people will be able, the simulators will be able to find this easily, because it's already very daunting simulations, and also if you have to tune it, become even more daunting. But actually, amazingly, it seems that they are seeing this. So indeed, we had some personal communications from this group that by performing this sort of tuning in 4 dimensions, they indeed seem to be seeing a new fixed point.
With only one additional tuning?
With only one tuning. And so whether this new fixed point is supersymmetric or not, they don't yet tell us. So because they don't yet know, they haven't yet measured the critical exponents. But anyway, I find that this is an exciting development.
So what about in 3? They tried to do that by tuning 2 extra.
Yeah, in three they don't see a new fixed point, and that's indeed consistent with what we expect.
I was saying, but wouldn't you expect that if you tune additional things, then you could?
No, because in 3 we predict there is no Parisi-Sourlas supersymmetric fixed point.
Oh, it should.
No. But that's a very simple thing to predict, because it just follows from dimensional reduction, from the absence in 1.
For the simulations that they did for the Gaussian distribution, do the critical exponents match your formula for either the dimension of 4 or 6?
Well, our theory does not predict critical exponents for non-supersymmetric fixed points, because our theory is only able to predict the existence of the instability. Well, we can try to go a bit further and compute, do some perturbation theory when these operators become relevant, but we haven't done this.
But the symmetric point, yes, you know.
For the supersymmetric, we know. So and of course, in 5D, everything is perfectly in agreement.
If they discover that there is.
Yeah. Of course.
You can say, look at the.
Well, they should have critical exponents equal to the 2D Ising.
Yes.
Yeah.
Okay.
Yeah. So that's the case.
So in the equal 4, without this additional tuning, this 50 conformal theory.
They see a theory, but it has critical exponents not equal to the 2D Ising without the tuning. Some new fixed point. Yeah, that's what they see. So there is another sign which convinces us that just 1 minute, it's a very short comment. So one more thing that convinces us that our theory is correct is what happens for the branched polymers. So the branched polymers are described, according to classic work by Lubensky and Isaacson, by the same theory, if in the n going to 0 limit, but with the cubic potential. And in that case, the numerical simulations show that the dimensional reduction from branched polymers that you can simulate to the Lie-Yang universality class in d-2 dimensions is perfect, works for any d. So this means that the mechanism for the loss of supersymmetry that I described here for some operators which become relevant, it should not be operative for the 5-cube potential. And so Apartim and Emilio, they did the same calculations that we did here also for the 5-cube potential, the same classification of operators, the same computation of almost dimension. And in that case, lo and behold, they find that all operators, including these ones, they only get positive anomalous dimensions. They didn't find any operator which get a negative anomalous dimension and can become relevant. So this is a very nice, again, agreement with results of the numerical simulations.
But I did have a question because the talk was extremely clear. Although it's not just a very simple question. So for t equals 3 without fine tuning, there's a fixed point.
For d equal to 3 without fine tuning, there is a non-supersymmetric fixed point.
Okay.
According to the numerical results.
Thanks again, the speaker.